Hello, I'm Mr. Bob and welcome to my Algebra 1 video series. This video covers Chapter 5, Section 1, titled Relating Graphs to Events. By the end of this video, you will have reviewed interpreting, sketching, and analyzing graphs. There are 3 sections and each covers one of the topics listed above. Your overall knowledge of graphs and understanding of them will be strengthened. If you'd like me to cover any of these topics in greater details, please leave your request in the comment section below. Please subscribe to this channel. If you find this video helpful, I would really appreciate it. Just hit that subscribe button. Thank you. Okay, objective 1, interpreting, sketching, and analyzing graphs. You can use an equation, an inequality, or a proportion to make a statement about a variable. You can use a graph to show the relationship between two variables. For example, you can use a graph to show how a quantity changes over time. So example 1, interpreting graphs. One student walks and takes a bus to get from school to home each day. The graph at the right shows the student's commute by relating the time the student spends commuting and the distance he travels. Okay, so we look at this graph here and it says we have a commute home, right here, the commute home. I'm going to pick a little darker color to get here. Where did my pencils go? There it is. It didn't switch. Go, there we go. Commute home. So what it is, this is from school to home, right? So over time, whether it's a half an hour, however long it takes this student to get home, he starts off, it says that he takes a bus. The student walks and takes a bus to get from school to home. So it looks like the student is going to leave school at quitting time, and he's going to walk, and you see the distance going home is gradually getting higher. Then it looks like the student's going to pause right here at the flat line, pause right there, waiting for the bus. Then the student will get on the bus, and the bus will go at a much faster rate home. It'll get to the point where the student will get off of the bus and then walk till he or she gets home. That's how we're going to look at that graph. And it says describe what the graph shows by telling each part. We just did that. Let's look at the bottom. Here it is. He starts off at a time 0, okay? And walking distance increases slowly. So the commute home, like I said, he's walking to the place where he's going to stop for the bus to pick him up, or her. Then the bus, he or she is stopped here, waiting for the bus. Then the student gets on the bus, and at a high speed or a higher speed, the bus takes the student home. The student gets off the bus and then finishes walking to home, finally at home. Okay. As you can see, the line is more vertical here for the bus. That means that the bus is going at a much faster rate than the student when the student walks. Okay, example 1, check your understanding. So this time you can stop the video, pause it, and give it a try. Just see if you can figure out what this graph is telling us based on what the problem tells us. So it says, the graph at the right shows a trip from home to school and back. The trip involves walking and getting a ride from a neighbor. Copy the graph and label each section. Okay, so why don't you go ahead and do that, and then when you get back, we'll do it together, okay? I'll wait for you. Okay, let's assume you've done that. So let's see if we can do the same graph and see if we can figure it out. So I don't have to necessarily do it, redraw it, but I guess maybe let me go ahead and do it. So it shows that we have a graph here oh, that's not too good. My hand hit the table here. Let's see if I can try that again. Let's see. We have an X, Y, and an X axis, and this is distance, and this is time, okay? And so we start to school at a walk, right? We're going to walk, and then we're going to get to a point where we're waiting for the neighbor to give us a ride. And then when the neighbor gives us the ride, we're going to go way faster, so the line is a lot steeper. And then we're going to be at school, so we're going to be at school during the day. We're not traveling any distance. And then we're going to get with the neighbor. The neighbor is going to be there after school We're going to get back in the car and we're going to get back here to the neighbor's drop off or pick off point. We're going to get out of the car and get ready, grab our luggage or our school bag and stuff, get out. So we're waiting a little bit of time and then we're going to take the slow trip home. I'll extend this graph a little bit. So we take the slow trip back home. So those are the steps. We get to the point where we're waiting for the neighbor, we get in the car, we go to school, we stay in school and get ready to leave school. Then we're down here at the bottom where we've gotten to the point to the drop-off spot for the neighbor. Then we get our things together and walk home and we finally get back home. So it's leave home in the morning and arrive back home at night. In example one, the distance, which is on the vertical axis, depends on time, right? So as you're walking, time's moving along and you're getting farther and farther along, right? And then that's distance from home. And then you get to school, and now time is going on, but you're not going any farther from home. And then at the end of the day, the time continues on, but now you start getting closer and closer to home, okay? Which is on the horizontal axis, it says. When one quantity depends upon the other, show the dependent quantity on the vertical axis. So that's what they're showing. We have an axis like this. So time is here and distance was here. So as we move along in time, the distance, so as we're going this way in time, the distance this way or back is a function of that time. So as we get time going along this way, then the distance can go up and up and up, or pause while the time is moving on, and go up, it can go back down, it can go over here, go down, it could actually go back up. It can do anything it wants. It can keep changing as time is moving on. So the time is constant, and you know that time is constant, moving along the hours of the day, and where the distance from home can keep varying, and that's the distance is measured on the y-axis. That's the vertical axis. That's what they want to call it. So we're measuring this is the independent variable time because it's going to go along no matter what we do, but the distance will depend. It's the dependent variable. It will depend on what we're doing, and it's measured against time, okay, and against the distance from a starting point. Okay, example 2, sketch a graph. So here it says a plane is flying from New York to London. That's a long flight. I don't know how many miles, maybe what, 4,000 miles maybe? Sketch a graph of the plane's altitude during the flight. Label each section. Well, we have the graph, and we're just going to talk about it here. So what happens? We take off, right? So down here is where we start off. We take off right here in New York. And then the plane, it doesn't go vroom, straight up, right? It kind of slowly kind of creeps up and just as time goes on, it gets higher and higher. And then it starts leveling off slowly till it gets to the flying altitude. This is the cruising altitude across the top of the earth over there to London. Okay, so it slowly came up. It got to you don't want to feel any fast jerks, right? So now we get halfway through the Atlantic, and now we're almost all the way through. We're at London, getting close to England, London, and we start low going. The plane starts going down slowly, and then it'll eventually kind of goes a little faster, but then it turns around and it starts leveling off because it has to like fly around the airport, right, to get a landing permit or whatever, and then they finally say, okay, go ahead and land. So that, and it starts coming down. It gets into wherever it has to be to get on the runway, and boom, now they're in London. So that's kind of how it went. So as time went on, the plane slowly went up, and then went at a constant elevation. Then it slowly went down and went down again and landed. Okay, check your understanding for example 2. Sketch a graph. Well, what's the problem they're giving us? Sketch a graph of the distance from a child's feet to the ground and the child's jumping rope, or the child jumps rope. So you get the up and down, joop, 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 joop. Child's jumping up and down, right? So the feet go up off the ground and then back down to the ground, right? Okay, label each section. So go ahead and give it a try. When you come back, we'll do it together, see how it comes out. Okay, I'm assuming you've done that. It's it should be a kind of a cute little chart as this child is jumping rope. So let's see, what is it? So I'm going to start off. I'm going to draw right here I'm going to draw the vertical axis. This is going to be time on the horizontal. And we're not even keeping track of time, are we? But on the vertical axis, it's going to be distance from ground. Distance from the ground, okay? Of the feet. So we start here, and the child starts jumping rope. So what is it? The rope goes over his head, and he jumps up, or she jumps up. And then the body slows down and starts coming down and goes speeds up a little bit, and then it boom, and now it goes up again, right? Is that what's going on? And boom. So the child gets higher and slows down and goes a little faster down. Boom. Goes up. This is jumping rope. That's exactly what, and then that repeats. That repeats on and on and on. So this is the height. That's the peak. Okay. This is the ground. Right there is the ground level. The peaks are right there and right there. That's when the body stops going up and starts going back down. You get the picture? It goes up fast in the beginning and then it slows down and then it comes back down, right? You've done that. You've all jumped rope. I'm assuming you have anyways. So that's pretty nice little drawing there, I think, of what's happened. Most graphs in this lesson do not have numbers along the axes. You can analyze the graph based on the shape of the graph alone. Okay, example 3, analyzing graphs. A car travels at a steady speed. Which graph could you use to show the speed of the car, and which could you use to show the distance the car has traveled over time, right? And explain. So let's look at these two. One has got a straight line. Everything is all, whatever the constant I is, and we're talking about speed here. This travels at a steady speed. So let's say this is speed, okay? 30 miles an hour, okay? And here's the time. Well, if I would say that a car traveling at a steady speed is this graph right here. I'm going to change the color to blue. It's this one right here because it's constant, it's steady. If this is 10, 20, 30, 40 miles an hour, okay, and you're doing 30 miles per hour, this is 30 miles per hour time. And which graph could be used to show the speed of the car, which could be used to show the distance it's traveled? Well, in this one, you have a car over time, and something's going up constantly. What's going up? Well, if the car is driving at this steady speed, right here, you're going to get a straight line. And what's the straight line going to do? As the car is traveling at a steady speed over time, it's going to get farther and farther and farther and farther from where it started. So this is distance, right here, distance. And this is the graph of the distance. Over time, it's getting farther and farther and farther. So here it's maybe 100 miles from home. Here it's 75 miles. Here it's 50 miles. Here it's 25 miles. And here's 0 miles from home. So as time is going on, maybe it's every hour that goes on, and we're getting farther and farther from home, if that's where we started. So we'll look at it then. Graph 1 indicates the quantity that does not change over time. This could be used to indicate the car is going at a steady speed, as we said. Graph 2 shows the increase over time, which could be used to indicate the distance the car travels at a steady speed over a given amount of time. And that's the steady speed is important. That's why the line is straight. The line here is straight. In the previous slide, I showed you the child jumping rope. The line went up and then it slowed down and then it came back and it went back up and it slowed down and came back. That was as the distance, as the time was going on, the height was slowing down and then getting faster and faster and faster down and then back up. So this is a constant speed here, and a constant change in distance on the second chart right here. Okay, example 3, check your understanding. Match the container to its graph. Suppose you pour water into each container below at a steady rate. And it's important, the water has to be going in, like water out of your faucet, right? You keep it at one speed. The water is going into your glass, at your cup or your bowl or whatever it is, at a constant rate. And we're talking about how fast what we're looking at here is how fast the water's rising in your container. So match the container to the graph that shows the change in height of the water in the container over time. It might start off fast and get slower and slower and slower, or it might be constantly going up, or it might change, go fast and slow and whatever, fast again, whatever. So let's look at, you go ahead and pause the video and try it, and then when you come back, we'll look at it, see what we come up with. Okay, so now that you're back, let's take a look. It's our last slide. Let's look at A. Well, A is a cup, and it has vertical sides, so, and a constant base size. So that means that as you pour water in here, it's going to go up like a ruler. It's just going to keep filling and filling and filling. And if the water going in at the same rate, the height of the water is going to raise. If this is just going to, every second you put in an ounce of water, it's just going to keep 1 more ounce every second. It's just going to go up constantly, straight. And that's what this line over here is showing. You put in some time, it goes up to a point, it goes up that high. You double the time, it goes up to here, and you go across. And now that the height is double, see, it's kind of like you double the time, which really should have been out here, and the height goes double. So this is the cup. It's linear. As you pour the water in, it goes up at the same rate. B, the bowl, starts off on a small flat surface way down here. And since the bowl is very narrow at the bottom, it fills faster than it does way at the top, which is the biggest it can be. So to go from here to here, or from going up, it might be 20 ounces. We're down here, it's 1 ounce. So that 1 ounce will go in real fast, but it's just going to take the time for 20 ounces to fill the top. And in the middle here, it might take 10 ounces. That's a 10 ounce to fill from a section in here over a period of time, right? So what's going to happen then is let's see, the bowl is going to start off fast because it's got a small bottom. And then as it goes up, it's going to get slower and slower and slower and slower until finally it's going very slow at the end. And that's what this does. It starts off fast and it right away starts filling more and more slowly as it's going. And just as the bowl curves up to going vertical, pretty soon, you see how it's going like that? It just finally very slow at the end. Okay? And so that obviously leaves C to be, well, let's mark it. So I said A is 3, so let's put the 3 in. Sorry for not marking it. I just said B is 1. So B is 1. Okay? So obviously that leaves C is being 2. C is going to be 2, but let's look at it. Why? Well, it's got a small bottom. It starts off filling and then slows down. The height going up slows down until it gets to the middle here. Now it's about the slowest it's going to go. And as soon as it passes the middle, it's going to start filling faster and faster and faster. So it starts off fast, slows down, gets to the middle, and it's going at a kind of a slower rate. And then as soon as it goes past the center, it goes, whoa, goes back up, so it's going faster and faster and faster. And then it's finally filled up to the top. And there's that.